I am very happy to see that a good number of viewers are ready to see my video lectures. And in my last class, I have discussed that how the reversible cell potential of this reversible cell could be determined by means of potentiometer, and voltmeter could not be used due to some different reasons. And next, I have also discussed how the cell potential is connected with this thermodynamic properties of the cell reactions. Today I shall work out some mathematical problems, how the thermodynamical properties of the cell reaction could be determined by using this cell potential. Before going to that, I like to mention one correction. In case of the Daniell cell is not a truly reversible one. This was discussed in my last class. One thing is missing when E is greater than E dash, means the cell potential is greater than the external potential or opposing potential. Cell reacts as galvanic cell and transported through this junction. Zinc is dissolved and copper is spreading out, but at this junction zinc ion is moving from left hand side to the right hand side, and the sulfate ion is moving from this right hand side to this left hand side, as sulfate ion in the right hand side remaining access as copper is getting out. But when E is less than E dash, external potential is greater than the cell potential, the cell acts as electrolytic cell, and the transporter through this junction now becomes copper is dissolved in the right hand side. So copper ion is moving from left hand side. Copper ion is moving from the right hand side. Copper ion is moving from this right hand side to this left hand side, and as the zinc ion is splitting out in the left hand side, sulfate ion remaining access. So sulfate ion is moving from this left hand side to this right hand side in order to make these two half cells electrically neutral. So this initial state of this Daniell cell is not being restored, so it is not truly reversible cell. Next, I like to mention also this Daniell's. Last class I have already deduced this one. The entropy change of this cell reaction is equal to NF d del E cell by del T. Or it is the discussions I am going to do, this temperature effect on this cell potential. So this d E cell integration and del S by NF integration and dt, the range is 298 Kelvin to T. And for the most cell reactions, when occurs in the condensed state, the delta S is very small. So this delta S have been taken as the constant one, independent of temperature. Only it will vary whenever the gaseous reactions participating in this cell. So this term is taken as the constant one, and here right hand side limit E 298 Kelvin means cell potential at 298 Kelvin and ET. So whenever the integration is made, so ET equal to E 298 Kelvin plus del S by NF into T minus 298 Kelvin. So this is the variations of this EMF of this cell with this temperature. With this temperature. So if we can plot, actually, if we can plot this one, then it is, suppose ET is plotted along this y-axis and temperature is plotted along this x-axis, and according to this equation, this will give state this one. If delta S is positive. And this one, this intercept will give you this E290 Kelvin. So this is the formula, and this is the graph by which this ET or EMF of this cell varies with temperature. Now I like to calculate the thermodynamical properties of this cell reaction by the use of this cell potential. And for one example I have taken, which is already I have discussed, which is very popular also, and this one is the standard Western cadmium cell. And this cell reactions is represented like this one: platinum, cadmium, mercury, cadmium amalgam 12.5%, solutions of this amalgams, cadmium sulfate, and this water crystallization, it is solid, cadmium sulfate, saturated solutions, and mercurous sulfate is solid, and mercury and platinum, it is the positive end, this is the negative end. Already I have discussed in my last lecture. So 12.5% have been taken, and to make the EMF of this cell actually remains constant. And the cell reaction is cadmium plus mercurous sulfate, and giving you this cadmium sulfate plus 2 mercury liquid, and this N for this reaction, N is equal to 2, means 2 gram equivalent of this reaction is participating. So ET, EMF of this cell is found to be 1.018 minus 4.06 into 10 to the power minus 5 T minus 298 Kelvin. And so naturally del E by del T at constant pressure equal to minus 4.06 into 10 to the power minus 5 volt Kelvin inverse. Now I shall show the thermodynamical properties. It is the free energy change, entropy change, and enthalpy change at 25 degrees centigrade. We like to calculate for this standard Western cadmium cell, which is already I discussed. This delta G means the free energy of this cell reactions. Equal to minus NF E cell, and this is equal to already given N equal to 2 and F equal to Faraday 96,500 coulomb, and this cell potential at 25 degrees centigrade is minus 1.018 volt. Volt into coulomb give you the joule, and see this value is coming minus 196,532 joule, and which is minus 196.5 kilojoule. Now the entropy change, delta G is always negative as the cell reaction is always spontaneous, and delta S equal to NF into d E cell by dt. Already this formula already I have done. And so the formula N equal to 2 and F 96,500 coulomb, and this d cell by dt is equal to minus 4.06 into the power minus 5 volt coulomb inverse, and this is given minus 7.8 joule Kelvin inverse. This shows that for this reaction, as the reaction is occurring in condensed state, so the delta S entropy change is very small, and this is why it has been taken as constant. and taken out of this integral sign. And delta H, enthalpy change of this reactions, which is also heat of reaction at constant pressure, equal to NF T d cell by dt at constant pressure minus E cell. So whenever putting the values 2 into 96,500 coulomb and T equal to 298 Kelvin, that's 25 degrees centigrade, and this is the temperature coefficient of this cell minus this is the E shell. Whenever we are going to calculate, this value is coming minus 198.81 kilojoule. And again, if we like to calculate the cell potential at suppose 30 degrees centigrade at 20 E 298 Kelvin is giving 1.0188 volt. If this one is the value at 298 Kelvin, we can calculate also the cell potential at 30 degrees centigrade, means 303 Kelvin, equal to this one according to this formula, and plus this is the entropy change, and 2 into F, the value of F here, and this joule Kelvin inverse by coulomb, it will give you this volt Kelvin inverse, and here 303 minus 298 Kelvin, and whenever the product is done, the calculation is given 1.0178 volt, means with the rise in temperature, the potential of this standard crystal dioxide is a little bit less. Now I shall give you another important problem. Suppose this standard electrode potential ferrous to iron, it is given equal to minus 0.44 volt, it is given suppose, and this E naught of a ferric to ferrous, this is also given 0.77 volt, and suppose we like to calculate this E naught ferric to Fe. What will be the value of this standard cell potential, standard electrode potential? So in this case, actually, for this reaction, this is the electrode reactions, and for this one, this is the electrode reactions. But some of the two will give you this electrode reactions, this one. But actually, the EMF, this EMF and this EMF could not be added up. Why? This is due to the fact that the EMF is the intensive property, and the intensive property could not be added up. So the intensive property could not be added up. It is very simple. Suppose one bucket of water having the temperature, half a bucket of water having the temperature 20 degrees centigrade, and if you add another half bucket of water with the temperature 40 degrees centigrade, but these two, whenever you are mixing this two half bucket of water, it will not give you the temperature 20 plus 40 equal to 60 degrees centigrade, as the temperature is intensive property. So naturally this cell potentials could not be added up. Cell potential could be converted into the free energy change, which is the extensive in nature, and extensive property could be added. So for this reactions, delta G1 naught, this is the free energy change for this electrode reactions, equal to standard free energy change equal to 2 into F according to this formula minus NFE cell in this case of the electrode, and minus 2 F and E naught Fe plus 2 Fe. And this value equal to minus 2F, and this value is given here minus 0.44 volt and equal to minus plus, and so 0.88 F volt. So for these reactions, ferric to ferrous, these reactions and free energy, standard free energy change of these reactions equal to this one minus 1 electron change minus 1 F Faraday, and this one value here. So this value is given and equal to minus 0.77 volt Faraday and volt. So whenever these two are adding, free energy change for this two electrode reactions are being added up, and this one equal to delta G naught, this one and this one, and giving this value and this value and minus this one equal to minus 0.11 F volt. So equal, and this for this reaction the free energy change will be minus 3F and the E naught ferric to Fe plus 3 to Fe. And so this value whose value we like to calculate, this value will give you this equal to minus 0.11 F volt divided by 3F. So this is the answer. So by this problem we learn that the EMF of the cells could not be added up. It is the intensity property, and it does not also depend on the mode of writing these equations, and the free energy change for these electron reactions could be added up to find the value of EMF of the cells.